Hey guys, let's take a look at how to do task 2 of the NMR challenge. So here we're given again the molecular formula, the proton NMR, and the 13C APT. So let us do the task. So the first step is of course to calculate the double bond equivalence or degrees of unsaturation from the molecular formula, which in this case is 0, as you can easily verify when you have 4 times 2 plus 2. So that's the expected number of hydrogen if there are no degrees of unsaturation, and minus 10, so that's the actual number of hydrogens present here, and that gives you 0. So you're going to have 0 double bonds, 0 rings. It's just going to be a saturated molecule. So the second step to take so that already limits our options to to very few isomers. And so another thing that we notice upon first glance at this problem is that there are exchangeable hydrogens here. Maybe let me change color. So exchangeable hydrogens are usually those attached to your oxygen, or those that can like exchange with a solution, because you have CdCl3, so basically the proton can just fall off and exchange with a deuterium here in a solvent, NMR solvent. So those are what's called exchangeable hydrogen, and usually their integrations are not very nice. So in this case it's 1.5. Not an integer. Doesn't mean that you have to multiply everything here by 2, which you need to do sometimes, but that's not the case. So we know that is probably just one exchangeable hydrogen because you only have one possible OH group in this formula. So we can just write down the OH group first because we know it's there. So we know this must be an alcohol and not an ether or things like that. So actually you don't have many options here left, but let's just take a look at the rest of the spectrum. So here you have 3 protons, 3 protons, so those are 2 methyl groups, and they are not necessarily next to each other, so we need to keep that in mind. And you have a 2 hydrogen peak here, so that's probably your CH2 group, and you have a single proton here, and that single proton is quite highly shifted, highly deshielded, so that's probably one that's quite close to the oxygen. So keeping that in mind, we only have 2 options that we can choose from because we need to have 2 methyl groups. So the first option is this, and the second option is this. So only one of it is correct, and that's when we need to take a look at the well, just looking at the shift, we know that this one is wrong while this one is correct, because you only have a single proton that's quite close to oxygen, and the proton is this one. And another thing we can see is the coupling constant. So let me just draw the correct molecule bigger for us to see. So this is the correct molecule, and let's take a look at the splitting the splitting pattern. We're not going to take a look at the constant yet because that's not necessary. So we have something here. So here there are 1, 2, 3, 4, 5, 6 peaks. So 6 peaks within the single signal. So these 6 peaks correspond to coupling to 5 other protons. So how is that possible? Well, we know this peak belongs to this hydrogen, and so it couples to 3 protons here and 2 protons here. But wouldn't we get a DT wouldn't we get a TQ or QT in this case? Well, because the coupling constants of this hydrogen with these 3 protons and this hydrogen with these 2 protons are quite similar, so it resembles a quintet. So that's why it is shown like this, and if you calculate out the numbers, you will see that these six peaks are not evenly spaced, and that basically tells you that while the coupling constants are quite similar, they're not the same, and therefore it is coupling to different groups. And another coupling pattern that is quite easy to check and to see is these two. So here we have a doublet and here we have a triplet. So we know that the doublet and the triplet both are methyl hydrogens. So we know that for this peak, the methyl hydrogens are coupling to two other protons. So we know that this peak here corresponds to this methyl group because there are two hydrogens here. And this methyl group corresponds to this methyl group because you only couple with one other hydrogen, which is this one. And if you see the coupling constant, okay, so maybe I should just talk about coupling constant now while we have an easier scenario to deal with. So the coupling constant is basically a value that is between the peaks. So basically this is, you take this number minus this number, and then you multiply it by this frequency, and then that will give you the coupling constant in hertz. And then if two things are coupling to each other, they will share the same coupling constant. So that's an overview of coupling constants, which I will probably talk about in another video because it's quite useful. But in this case, we don't need coupling constant to work out the actual solution. We just need to see the shifts, and to confirm our guess is correct, we can just look at the splitting pattern rather than the constant themselves. And maybe we should also take this chance to make sense of the 13C APT spectrum. So as usual, we identify the CDCl3 peak. So I forgot to mention this is probably a CDCl3 peak as well. So like the website didn't label it, but we should know it's CDCl3. And for the 13C APT, basically when you see three lines very close to each other, and around the same height, it's usually CDCl3. And because it's APT, we know that because CDCl3 contains 0 protons, deuterium is not your hydrogen 1 proton, so it is not counted. So if it points up, then basically everything that points up here correspond to carbons that are attached to an even number of protons, and these are the carbons that are attached to an odd number of protons. So we can see that this peak here should probably correspond to this carbon because one, it is highly deshielded, and the other thing is that it is pointing in the odd direction, which means it's attached to only one proton. Okay, so let's take a look at the other few peaks. So here we have only one even proton carbon here, so that corresponds to this one. And if we assign the other two, we know that this carbon here is closer to closer to the oxygen, so it is probably more highly shifted, so it should probably correspond to this peak, while the last one, this carbon, should probably correspond to this peak. And so we have fully assigned the spectrum, and I hope that's helpful, and I will continue with this series when I have time. So bye.